Okay, we're welcoming Kyle Davidson, a former Stewart alumni and John Glenn alumni, and now a NASA astronaut to share with us today about the engineer, an NASA engineer.
I appreciate the upgrade.
Okay. All right, Kyle, you know what I'm saying. So, Kyle, tell us about your responsibility.
Oh, good morning, Stuart, and good morning, students. So, as Mr. Bernard pointed out, I'm a alumni of Stewart Middle School, as well as the John Glenn Top Gun Academy. I am a current engineer at the NASA Kennedy Space Center here in Florida. I actually work the commercial crew program as a supporting engineer, as well as the launch services program. The commercial crew program, for many of you that know, SpaceX and Boeing are two of our commercial providers to return crew and astronauts to the International Space Station from U.S. soil. We've successfully launched 2 crewed missions from U.S. soil in 2020. And then we have more planned for this year, including the inaugural flight of the Boeing Starliner capsule with crew for their crewed flight test. I've also supported our launch services program, which provides mission support and insight for various launch providers, SpaceX, Boeing, ULA, the Atlas V Delta family of rockets under them, as well as the Falcon 9 and Falcon Heavy vehicles under SpaceX, and the upcoming Blue Origin development process. But one of the key things about the launch services program that I support is we actually help to support the launch of the Mars 2020 Perseverance rover that launched last year and which is landing on Mars today. So I'm going to go through a little highlight of the expected plans for that mission, as well as what you can expect to see today if you tune into the NASA live stream on YouTube and a variety of other different sources. So without further ado, I'm going to pull up a little presentation here just to kind of show you guys a little about the Mars 2020 mission. And Mr. Bernard, can I get a confirmation when that is on your screen?
Hey, Kyle, you are clear to go.
Clear to go. Okay. All right. So Mars Perseverance. Now, the mission for Mars Perseverance as a rover is complicated. There's a lot of different science that's going to be going on, but suffice to say, we have a few key objectives that have been part of the mission from the get-go. At a high level, this involves exploring a geologically diverse landing site, which we've selected and the agency has selected based on a number of gating criteria based on expected scientific outcomes. We're trying to assess the ancient habitability of Mars. And what that means is we're looking to see what life could have been sustainable on Mars millions of years ago, when Mars likely had water, an atmosphere, and some other habitable conditions that may have allowed life to thrive. Additionally, we're going to seek signs of ancient life, particularly in some special rocks that are known to preserve signs of life over time. These are either fossilized, microscopic components, bacteria, or other organisms that we suspect may be fossilized within those rocks, and collect some of those samples so they can be returned to Earth by a future NASA mission. We're actually going to be collecting those samples in some sealed containers and then depositing them from the rover at specific points along its journey. And then finally, we're going to demonstrate some new technology that will potentially help with future exploration of Mars, both from a robotic standpoint and a human exploration standpoint. But how do we get there? So the journey to Mars is something that a lot of people sometimes take for granted. If you look at this nice little diagram here, you can actually see a pretty scaled up version of the distance between Earth and Mars within orbit. So not all of this is to scale, obviously, but the idea is to show here some relative changes in the timing it takes to get to Mars. Now, when we launched from the surface Earth of Cape Canaveral last year, July 30th, we aimed for Mars when it was kind of ahead of us in its orbit. And the reason we do that is because there's obviously a long time between the points from when we launch to Earth to when we arrive at Mars. It's about a 6-month journey. So the reason is we have limitations in how fast we can get there. If we're carrying a big heavy payload such as a rover, we have to optimize our efficiency. So we actually have to time the event within a very narrow window to manage to get to Mars for these specific missions. Some missions we can go a little bit earlier, some missions we can go a little bit later, but for a lot of the missions that we have to other planets require precise timing that has to be calculated and accounted for well ahead of time. So the opportunities to launch to Mars occur maybe every 26 months, so about every 2 years. So if we miss the opportunity, we have to wait for a whole another round if we want to go for another cycle. So I put these distances up here just to kind of give you some perspective. So at its closest point when we launch to Mars, about 100 million kilometers away. As a result, because of the travel time and the distance and that amount of time that we have to get there, it takes about 6 months to get to Mars. Earth is going to change position as well as Mars are going to change position. So when we're at arrival, which is about now, we're only about 130 million kilometers away. So not a big change there from a distance perspective. But if you notice, the distance we've traveled is much larger. So approximately 300 million kilometers is how long the Perseverance rover and the Mars orbiter and everything is going to have to travel to get to Mars in that time frame. So it's actually traveling pretty substantially further than the distance it actually is between the two planets in a launch scenario. And we're aiming, if you look in that upper right-hand picture, we're aiming for a really small site that's actually a pretty large crater, but we're aiming for a small site within that crater. It's about 4.5 by 5 miles wide. It's a very, very small point of aim. And we're doing that because we're testing some new technology. So I'm going to explain the landing process a little bit to you because this is a really complicated point in the sequence of events to get to Mars, particularly for this rover and the sister rover that came before this, Curiosity. So it's colloquially known as the 7 minutes of terror because the entire process takes about 7 minutes. So about 10 minutes before entering the atmosphere, the cruise stage and the shields and everything that kind of housed the rocket or the spacecraft and its various components up here in the upper left-hand corner, if you can see my mouse, this is going to separate. And this provided us all the commodities and a lot of the tracking and necessary adjustments that we could get to Mars along the way. So there were little adjustments that had to be made. Sometimes there's some points where we can make those adjustments and kind of fine tune the trajectory to get where we need to go. But in essence, once we get to that point, we're dropping that stage off and we're committed to going into the atmosphere. So once we go into atmospheric entry, all of these components, the heat shield, the rover, the sky crane or descent stage, and the back shell are all coupled together and are going to start busting their way through the atmosphere. And that heat shield is going to play a major role in protecting us from the thermodynamic events that occur. We're providing a lot of shielding to the spacecraft and everything around it because we don't want them to get damaged by the heat and the pressure that builds up during that entry. But Mars's atmosphere is kind of tricky. It's a little too thin to maximize every bit of drag that you would normally get with Earth's atmosphere, which is nice and thick, but it's still prevalent, so we can't land like we can on the moon where we just use or other atmosphereless bodies where we don't, we can utilize thrusters and kind of control everything that way. So we have to use a combination of all the technology that we have from Earth and kind of the non-Earth atmosphere type of landings to make it work for us. When we go through that atmospheric entry, the heat shield's going to reach about 2,300 or so degrees Fahrenheit, about 1,300 degrees Celsius, which is pretty significant. That would melt a lot of materials, but we have the materials designed such they can withstand that, or they can ablate away. You often hear the term ablate of heat shields, where some of the material is actually made to break away and take and shed some of that heat as it re-enters. So as we begin to get through the atmosphere, there's going to be some guidance and control systems on that back shell that are actually going to adjust and tweak the trajectory all the while to the pre-staged points along its flight path based on where we need the rocket to end up, where we need the spacecraft to end up at the end of its journey. When we get down below about 1,000 miles per hour, about 1,600 kilometers per second or per hour, the parachute's actually going to deploy. And the parachute actually is being designed to deploy at a supersonic speed. So that parachute is, again, working in a much thinner atmosphere than we would here on Earth. But we've designed it and even tested it on Earth in some certain ways so that we can replicate the environment that we expect it to endure during Mars re-entry. So once that parachute deploys, that's going to send us down even further, but it's still not quite slow enough, and we can't rely on the parachute to bring us to a nice soft landing. So the parachute itself is pretty big, though. It's about 70 feet in diameter, and it's going to deploy about 240 seconds after entry. So we've got a pretty good amount of time that we're going to be re-entering the atmosphere using just the heat shield, and then we're going to go right into that parachute deploy. So at 240 seconds into re-entry, we're going to deploy it, and we're about 7 miles above the surface. So we're still going to be going pretty fast, and we still got a lot of time to go. So roughly after the parachute lands, about 20 seconds or so, we're going to be dumping the heat shield and starting to look for the landing site. So there's going to be a variety of optical sensors, radar, that are going to be trying to track based on preloaded maps that are saved in the spacecraft's database where we need to go and what we need to do to adjust. And all the while, that's going to be calculated and itemized, and all of that data is going to be fed into the spacecraft while it's working. There's about a 7-minute delay from the time that these communications start to when we receive them on Earth. So we do not have the ability to control this live. This is all pre-programmed, and this the spacecraft trying to figure its way through the problem. So a lot of this required intensive planning and a lot of practice and a lot of lessons learned from the early Curiosity rover landing. Now, once we've descended to about 200 miles per hour with the parachute, again, we're still coming a little too fast. So what we're going to do is drop this descent stage, which houses the Perseverance rover together as one unit. And this is going to fall away and kind of jettison out of the way of the parachute and the heat shield that have been separated so that we don't run the risk of them re-impacting. And this sky crane activates these rocket thrusters on the perimeter that will now actually descend and provide a power descent to the entire connected assembly. So this is going to take the remainder of that speed and slow down to a much, much safer descent velocity. So that's about 6,900 feet or so above the surface that's going to happen to break from the back shell and heat shields assembly. Now, the descent stage is where this gets probably the most tricky. We are actually going to have the descent stage slow to a final descent speed of about 1.7 miles per hour, which then initiates this sky crane maneuver. And while it's not drawn here, there's essentially a variety of rigging material and, for all intents and purposes, cables or slings that will rope down onto the Perseverance rover and suspend it in midair. And it's going to be about 66 feet above the surface that the rover is going to get descended down on cables that are about 21 feet long. So we've got a couple more feet to go, and that rover is then going to touch down, being suspended in midair by the sky crane. And once that rover has sensed that it's touched down based on all of its wheels and deployment, the sky crane is going to shoot off and go at a safe distance so it doesn't risk re-colliding with the rover. So what that all looks like is, I've got a nice little video here to show you guys so you can get an idea of what that entire sequence of events is going to look like. Again, it's going to take place in about 7 minutes. The video is a little bit shorter, but you can get the idea. There's a lot going on in that 7 minutes. And just checking, Mr. Bernard, do we have video?
No, sir, we do not. Well, we have video. We do not. Is there audio with it?
There is. It'll be very quiet.
Okay.
I'm going to turn it up to see if that may help. Ooh. Sorry. So the set stage and back shell are all going through the atmosphere. Heat shield is protecting us as we re-enter from the intense heat. Meanwhile, the guidance controls are going to stabilize that entire setup. Parachute deploys. Start to decelerate amongst our descent. Heat shield gets separated and falls away to its existence. Descent stage comes out, moves out of the way of the back shell, and starts to look for its landing site. Crane deploys, rover lands, confirmation, separation. Sky crane goes away to a nice safe distance where it won't run into our rover as it continues its diagnostics and setup. And we're on Mars. All right. Everybody able to see the video just fine? So some details about our landing site. So just to give you guys a time frame, touchdown is at about 3:55 p.m. this afternoon, Eastern Standard Time. The new home for the rover for Perseverance is the Jezero crater, which is a impact crater about 28 miles wide. Oh, I heard a question.
No.
Oh, sorry, no problem. Just north of the Martian equator. So some quick trivia for you. Perseverance is actually only the 5th NASA rover to attempt landing on Mars. We've had quite a few other landers that have landed and maintained stationary science outposts and some orbiters around Mars, but we've only ever had 5 rovers that have attempted to land. So it's a pretty significant milestone, obviously, to have any rover successfully land. But you know, we are always counting on our team to do their best to determine every possible way things can go wrong and to identify those and fix those ahead of time. So we are still crossing our fingers today, but it's going to be an intense witness one way or another to watch this rover land. So I mentioned before that the aiming point that we're going for is pretty small. It's only about 5 by 4 miles across. And to just put some perspective based on that original map that we had, this is basically the equivalent of throwing a dart at a moving car while trying to hit a mosquito on the window. And the whole time that car is in Orlando, to just give you an idea on the distance and scale that we're looking to try to accomplish with this rover. So it's a massive undertaking to be able to plan for this type of work, and it usually occurs, you know, months to years ahead of time to come up with all the conditions and determine exactly what you're going to do, and for good reason. We've got a lot of science that's going to be going on this rover. We've got subsurface scanners that are going to look underground using radar, which is a new method to try and scan and look for materials, water, and the like, and understand stuff below the surface where our tools and access via physical means may be limited. We do have additional tools for analyzing chemical makeup of some of the surface materials, so taking samples, studying them, looking what the different components of the surface material is made out of. We actually have an experiment called MOXIE, which stands for the Mars Oxygen In Situ Resource Utilization I may mess up the acronym a little bit, but the idea is this experiment's going to actually produce oxygen from the atmospheric carbon dioxide on Mars. And this is in part understanding if we want to send people to Mars, we're going to need oxygen to breathe. So what can we do to potentially extract that from what we have? Additionally, I mentioned it before, we're going to be collecting samples in sealed containers, and we're going to potentially return those to Earth in the future, either utilizing a robotic mission to retrieve them or having people that will actually go to Mars and bring them back for us. We also have a stowaway on board, to barter some pyrotechnic terminology. We have a tech demo called Ingenuity, which is a Mars helicopter. So this is going to be the first test of a powered flight vehicle on another planet. So this has never been attempted before. It's all new. There was a lot of development that worked to try and make this helicopter work. You gotta remember, Mars's atmosphere is not like ours. It's very thin. So we need to find ways, if we want to survey stuff a little bit faster and potentially use these to augment human and robotic exploration, we had to really come up with creative ways to try and determine how we could get a vehicle to fly on Mars when we have less air to push against. So right now, the plan is for this to fly for potentially up to 90 seconds, with distances about 980 feet horizontally, but only about 10 to 15 feet off the ground. So help prevent, if there is an issue, we can have a power descent and try and figure what it is. Don't risk the rover crashing, but gives us a good idea on how far we can go with the helicopter and Ingenuity. The helicopter will fly on its own. So again, the delay between Earth communications and Mars communications is pretty substantial. So we have to program all the commands to fly the vehicle ahead of time, and it's going to do all of it on its own, or it's going to augment that through some of its sensors. So how can you watch? So today, again, February 18th, 2021, 2:15 is when a lot of the live streams are going to start. So YouTube, Twitter, Facebook, all the main social media sites, we're going to have live streaming up, as well as NASA TV. You can go online and start watching some of the commentary. They're going to explain some of the stuff that I just talked about and go into more detail on some of the important science aspects of the mission, some of the other payloads. We even have a clean feed of mission control, so you can just see what's going on in the control room as everybody's starting to get tense. When the Curiosity rover landed back in 2012, it was a real tense moment there during that 7 minutes of terror. And when everybody saw that the rover had successfully landed, you saw probably the happiest group of engineers at the time on the planet. So it's absolutely entertaining to see the team that's worked so hard on this project continue to reap the rewards of their success in science. You can also hashtag Twitter on Countdown to Mars. The clock is ticking. It's only a few hours away, so I fully expect a lot of you are going to tune in. It's going to be an exciting moment for all. So with that being said, go Mars Perseverance, go Mars Rover 2020, and hashtag Countdown to Mars. So I appreciate your time today, Stewart students. Look forward to you tuning in, and good luck and many successful years to all of you ahead. From a previous Stewart alumni, and wish you all the best.